Nature rarely draws in straight lines. Rivers wind, hills roll, and planets bulge. But our mathematical tools to measure them are rigid, flat, and straight. When we look at a basic geometric diagram, calculating a square or a triangle is easy. The formulas are simple: length times width, or half the base times the height. They provide an exact answer in an instant. But human infrastructure eventually outgrew simple boxes. Modern engineering relies on massive domes, winding highways, and sweeping overpasses. We are often trapped trying to calculate the true scale of a curved reality using mathematical rulers that refuse to bend. For an architect or an engineer, the stakes of this mismatch are high. If you're preparing to pour concrete for a massive curved project, you must know the absolute exact area to order the right amount of material. A rough guess leads to disaster. Overestimating blows the budget, while underestimating leaves a structure without enough support to stay standing. How do you measure the exact continuous area of a curve when every physical ruler and geometric formula relies on straight lines? To solve the modern engineer's dilemma, mathematicians had to invent a conceptual cheat, a method that breaks the rigid boundaries of standard geometry. The workaround starts with a trick of substitution. To measure a curve, you pack it full of a shape you already know how to measure, the rectangle. You can see this logic in a circle. By slicing it into thin triangular wedges and interlocking them, we approximate a large rectangle. This structural hack allows us to derive the area of a circle as pi times the radius squared. This proves that straight-edged pieces can provide an estimate of curved areas. But for real-world engineering, an estimation is not precise enough. Take the curve f of x equals x squared. To find the exact area between 1 and 2, we pack this space with vertical rectangles of width dx. But because their tops are perfectly flat, they stick out or leave empty spaces beneath. This blocky approximation leaves dangerous gaps in the measurement. Summing these rectangles creates a result that is inherently inaccurate. The solution is to increase the resolution. By decreasing the width of dx, we can pack more, thinner rectangles into the same space. Watch the accuracy improve from 50 thick rectangles to 5,000 hair-thin ones. The jagged gaps shrink, hugging the curve closely. Now, what happens if we shrink the width of dx down to 0? The number of rectangles becomes infinite. This state, the limit of the sum as it approaches infinity, is where all gaps are eliminated. This is the definition of an integral. We represent this exact area with an elongated S symbol. It is the mathematical shorthand for a smooth sum of infinitely small areas. By pushing a basic geometric trick to the absolute threshold of infinity, mathematicians unlocked the exact area of any continuous curve. That elongated S is the exact tool engineers use to calculate materials for massive curved structures, like the dome of the Golden Temple. It also determines the length of a heavy cable drooping between distant electrical substations. Integration provides the mathematical blueprint required to safely build physical infrastructure. This logic of summing infinitely small pieces reaches far beyond physical shapes. It applies to any continuous accumulation over time. In medicine, doctors use integration to track the accumulation and dissipation of drug concentrations in a patient's bloodstream over the course of a day. Computer engineers use the same principles to calculate the rate of digital data accumulation on server hardware and hard drives. Integration acts as the powerful mathematical engine that translates the messy, continuous, beautifully curved reality of our physical universe into the exact numbers we need to safely build, heal, and innovate.